Hello everyone, it's my pleasure to share the research work of my team on real-time kinematic, virtually from China. I'm Han Gao, working at Raman Lab of Huawei Technologies in China. Today, I'll present my work on applying the factor graph optimization for post-processing RTK. The presentation will comprise 4 parts. The first part will introduce the urban navigation challenges for RTK. The second part will introduce the factor graph framework for real-time kinematic and then go into details. The next 2 parts will present the experiment performance and draw the conclusions. Nowadays, the autonomous system uses multiple sensors for both online navigation and post-processing mapping. These sensors include GNSS, LiDAR, camera, radar, wheel odometer, and so on. Among them, GNSS is the only one that can provide absolute position constraint. So, the autonomous system relies on GNSS RTK for precise global position estimate. However, in urban environment, the surrounding building produce signal blockage, non-offset reception, and multipath interference. All these phenomena may poor signal quality and availability. This degrades RTK performance and makes RTK hard to obtain fixed solutions in urban environment. Lack of fixed solution, the consequence for autonomous system is that the system has to rely on other sensors such as MU and wheel odometer to make relative position estimate. This would produce bias in long term. The left figure is an example of failed LiDAR mapping results. The vehicle travels along the street for twice and relies on only MU and LiDAR for navigation due to a miss of RTK fix. From the LiDAR scanning points, we can clearly find double scanning surface, which is actually from the same building surface. Conventionally, real-time kinematic is achieved by extended Kalman filter. The forward version of Kalman filter is used for online positioning, and the forward and backward version is used for post-processing, also known as combined RTK. In recent 3 years, researchers from different groups investigate on applying factor graph optimization for GNSS and has obtained promising experiment results. Factor graphs has been treated as an alternative framework for solving estimation and optimization problems and has been widely used and proven to be very beneficial for a plenty of applications in SLAM and robotic domains. Compared with Kalman filter, there are some advantages for factor graph optimization. The first one is that factor graph optimization has better linearization. This is due to multiple iterations for each epoch. The second point is that it has better time correlation because it doesn't follow the Markov process assumption. The third point is that the framework of factor graph optimization is much easier to be integrated with other sensors, such as LiDAR and cameras, no matter the size of their features. On the other hand, the most disadvantage for factor graph optimization is its high computation load. This is due to more iterations than EKF for each epoch. So in this research, we apply factor graph optimization for post-processing RTK because for post-processing RTK, it's a task requires more on the performance of global optimization but requires little on computation loads. In the next section, I'll introduce the framework of factor graph optimization for real-time kinematic. The factor graph optimization is achieved by minimizing a global cost function defined by different variables. There are two types of variables in factor graph. One is the state variable, which is to be estimated by factor graph optimization, and another type is the factor, which encodes the constraints applied to the state variables. I'll introduce the factor graph framework in this slide briefly, and then I'll go to each factor in detail in the following slides. First, the state variable represented by capital X include the positions in ECEF frame coordinate, and also the single difference ambiguity of each received satellite used for integer ambiguity resolution. For factors, they are represented by different colors in this figure. There are 5 kinds of factors. The green and orange factor represents the double difference pseudo-range and carrier phase measurements for RTK. They are differenced by the reference satellite, which is indexed as 0 in this figure. And the blue factor is the motion factor, which provides the constraints between two state variables, actually the positions between two epochs. The purple factor provides the double difference ambiguity constraints between two epochs, and the yellow factor provides the constraint of the single ambiguity of each received satellite for each epoch. After obtaining the state variable estimated by factor graph optimization, the results will be applied for the integer ambiguity resolution method, epoch by epoch, to obtain the final RTK results. Next, I'll introduce each factor in detail. The state to be estimated at each epoch comprises 2 parts. The first part is the relative position in ECEF coordinate between the rover and base station. And the second part is the single difference ambiguities of each received satellite, and their covariance output will be used in lambda later to search for the integer ambiguity. It is important to state here that why the single difference is used instead of the double difference ambiguities. Although they are equal in mathematics, but in reality, it is very common in urban environment that some satellites will be disvisible or newly visible in such environment, so this will cause the frequent changes of the reference satellite. And the single difference ambiguity estimation is more convenient to deal with the handover of the reference satellite than the double difference one. So that's why the single difference ambiguity of each received satellite is used in state estimation. Next, the motion factor. The motion factor is used to constrain the relative position changes between two neighbor epochs. Its corresponding error function is calculated as the difference between the estimated position changes and the measured position changes. And the estimated position changes is just the difference between the position estimates, the position state to be estimated, and measured state changes can be obtained from the weighted least square velocity from satellite Doppler measurements. Next are the double difference, pseudo-range, and carrier phase factors. Double difference is the core of real-time kinematic. Different errors can be eliminated by double differencing to obtain high precise positioning. For For received satellite signal, there are different arrow sources. From the satellite to the receiver side, they are the satellite orbit arrow, the satellite clock arrow, atmosphere arrows, including ionosphere and troposphere arrows, and also the received clock bias. By a single difference for the same satellite between the rover and base station, the satellite orbit arrow and clock arrow can be eliminated, and the atmosphere propagation arrow has been mitigated. And by one more difference with the reference satellite double difference, the clock bias offset between the rover and base station can be further eliminated, so leaving only the ambiguities for carrier phase. Now back to the factors. The calculation of the double difference pseudo-range residual is obtained from the difference between the measured double difference pseudo-range and the estimated double difference pseudo-range. The estimated double difference pseudo-range can be obtained from the unidirection vector of two satellites and the relative position between rover and position. The calculation of double difference carrier phase factor is similar. The calculation of its residual is more or less similar after changing into meter unit, except for the term of the single difference ambiguity term between the current satellite and the reference satellite. Next, the single difference ambiguity factor term. As we stated before, the single difference ambiguity is defined in the state variables because it's more convenient for handover reference satellites between different epochs. And here, the single difference ambiguity factor is defined to take constraints on the absolute values of single different ambiguities. Because without this factor, there's no constraints of the ambiguity term of the reference satellite. So, its single difference ambiguity will go towards zero in factor graph optimization. In the calculation of the arrow function, its residual is calculated from the single difference carrier phase and single difference pseudo-range measurements, and these two measurements have been used to constrain the ambiguity sum of different received satellites. And one arrow function, cost function, at each epoch will be defined for a bunch of satellites that are with the same constellation and frequency. For example, so one cost function will define at the current epoch for GPS L1, and another arrow function will be defined for GPS L5. Next is the double difference ambiguity factor. According to the nature of GNSS tracking loops, the integer ambiguity tends to be constant once the satellite signal has been effectively tracked. Therefore, the double difference ambiguity between the same satellite and the reference satellite that track in multiple epochs should share the same ambiguity values if there is no cycle slip has been detected. Based on this assumption, the double difference ambiguity residual has been defined as the difference of the same double difference ambiguity at different epochs. There are three methods correspondingly used for cycle slip detection. They are the receiver LLI indicator, the pseudo-range and carrier phase combination to detect cycle slip, and also the geometry-free combination for dual frequency receiver to detect cycle slip. By now, this is the factor graph Framework for RTK. The RTK flow solution is first calculated by factor graph optimization. Based on its solution, the integer ambiguity is resolved epoch and epoch, and this framework is similar with the continuous version of combined EKF-RTK. The problem with this framework is that the integer ambiguity has been resolved independently between epochs. However, by nature, they are actually time-related. But in this framework, the resolved ambiguity has not been helpful for ambiguity resolution at other epochs. To resolve this problem, the second optimization is applied to hold the fixed integer ambiguities in the last optimization. In the improved framework, if the ambiguities has been reliable fixed in the first optimization, the RTK fixed result will be taken as known variables in the second optimization, and additional factors will be taken to constrain the single difference ambiguities between neighbor epochs, so that in this way, the fixed integer ambiguity can be held in the optimization and higher fixed rate of RTK could be achieved. The third part is the experiment performance. The proposed algorithm by FGO and second optimization are tested and compared under a piece of medium and deep urban environment in city of Guangzhou. The test rule is as long as about 1.5 kilometers. The rover receiver on test vehicle is a navigation level receiver with dual frequency of Beidou and GPS constellations, and the base station information is provided by Qianxun VRS service. This is the performance comparison between extended common filter and factor graph optimization. The EKF-RTK is achieved by RTK leap in combine and fix and hold mode. By comparing these two results, we can clearly see that the factor graph optimization results is more smooth and less affected by the unlocked receptions in very deep urban scenarios. However, its fixed rate is much lower than the EKF equivalent. The EKF-RTK achieved 57% fixed rate, while the FGO-RTK only achieved 46% fixed rate. But after the second optimization, the fixed rate has been improved to about 68%. The position error has also been plotted in the following figure. It can be seen from the figure that the errors after the second optimization have also been reduced compared with the FGO-RTK output. In urban, it's very common to have a false fix output from the algorithm. The position errors within a wavelength is supposed to be a true fix. I also figure out the true fix rate, which is about 63%, and this indicates about 4% of the fixed solution at the second optimization are false fix solution. Finally, the conclusions. First, the FGO-RTK positioning results are smoother than EKF-based RTK. The FGO-RTK is similar with the continuous version of combined EKF-RTK, and its fixed rate is lower than fix and hold version of combined EKF-RTK. After second optimization strategy, the RTK fixed rate can be largely improved. The further research work can be conducted in terms of accuracy, efficiency, and reliability. In terms of accuracy, the odometer-aided RTK should improve both the positioning accuracy and also fixed rate. The odometer can be time differential carrier phase, inertial sensors, wheel odometer, camera or LiDAR features. In terms of efficiency, sliding window strategy was a try for real-time implementation RTK. The success fixed solution determination is required to improve the reliability of RTK in urban environments. That's all I have to say. Thank you for listening.